Chapter 1, Section 4, Learning Target 2, deals with interpreting position time and velocity time graphs. Here you see 4 different position time graphs, each graph representing an object with a different type of motion. To figure out the type of motion represented, we need to look at the shape of the data line on the graph. Let's start with one that is familiar to us. When we have straight lines on a graph, that means the object has a constant velocity. This graph also has a constant velocity, but since this line is horizontal, the constant velocity is equal to 0. Now let's look at the top 2 lines. They're not straight lines, they're curved lines, which means their velocity is not constant, their velocity is changing. But how is it changing? This graph has a steeper line at the start. The line gradually gets less and less steep. That is telling us that the object is slowing down as time passes. The velocity is decreasing. The object could be coming to a complete stop. On the other graph, the line is getting steeper and steeper and steeper as time passes. So this object is speeding up. The steeper the line, the faster the object is traveling. The greater the velocity is. Here are the 2 graphs we were just looking at. The object on the top left in that position time graph is speeding up, and the object on the top right is slowing down. Now we can take the information from a position time graph and we can make a velocity time graph with it. The top left graph, when drawn on a velocity time graph, has a straight line that is angled up. Since the position time graph shows that the object is speeding up, that means the velocity is increasing. A line that is angled upward on a velocity time graph shows an increasing velocity. The velocity is getting greater as time goes on. In the graph on the right, the object is slowing down. To show that the velocity of an object is slowing down, we would create a line that's angled downward. On this graph, it's showing that the velocity is decreasing as time goes on. This slope is negative, which shows a change in the velocity, meaning the velocity is slowing down. If a position time graph shows that an object is speeding up, the shape of the line on a velocity time graph is always going to look like that. If on a position time graph the object is slowing down, the shape on the velocity time graph is always going to look like that. So you can start figuring out these graphs by figuring out the patterns. These graphs always go together. When we were looking at objects with a constant velocity, we said you could find the slope of the data line on the position time graph to figure out what the actual velocity was. With objects that are speeding up and slowing down, since the line is curved, we can't find the slope of the entire line, any 2 points on the graph. What we need to look at is the slope of what's called a tangent line. The tangent line is a line that touches the curve in only one spot. We can find the slope by taking the rise, which is the change in position or distance traveled, and the run, which is the change in the time, and we can figure out what the velocity is, just like we've done before. You're finding the instantaneous velocity this time, the velocity at that specific point. Here you see a velocity time graph for an object that is speeding up. The velocity is increasing. We can also find the slope of this line, and that tells us some specific information. In this case, the slope of the line tells you the acceleration. When you find rise over run on a velocity time graph, the rise is the velocity, the run is the time. So you can find any 2 points on this line because it's a straight line, do rise over run, and you're going to figure out the acceleration of the object. So on a position time graph, the slope tells you the velocity, and on a velocity time graph, the slope tells you the acceleration. Page 64 in the reading provides a comparison between the position time graphs, velocity time graphs, and acceleration time graphs for different types of motion. Here you can see how the graphs compare. In the first column you have a car that is at rest, which has a position time graph with a horizontal line because the position does not change compared to time, which gives us a graph here where the velocity is 0. So our data line would be right across at 0 velocity. And here the acceleration is 0 because the acceleration isn't changing. The speed isn't changing. The object's not speeding up or slowing down. There is 0 acceleration. The object is just standing still. In the next column, this car has a constant velocity. So we see that the line is angled upward. It's a straight line showing constant velocity. That gives us a velocity time graph with a horizontal line, but not at 0, because this car does have a velocity, and the velocity is constant. In this case, the acceleration is also 0 because there is no change in velocity. The car is moving with a constant velocity, no changes. In the third column, you see an automobile which is accelerating. Here, the car is speeding up according to this graph, which means that there is an increase in the velocity, which we see on this graph. The line is angled upward because the speed is increasing. Because the speed is increasing, there is an acceleration. There's a constant acceleration. The velocity is changing at a constant rate, which we see from the slope of this line. And so we do have a horizontal line for the acceleration graph, showing that the speed is changing at a constant rate. When you compare the graphs of motion, you'll notice that each graph stack, as we call it, shows the same kind of motion. Each graph simply focuses on a different aspect of that motion. The position time graphs show changes in position, which tells you something about the velocity. Velocity time graphs show changes in the velocity, which gives you information about an object's acceleration. Acceleration time graphs show changes in acceleration. However, for the work we're going to be doing, all of the acceleration is going to be constant. So we will only have horizontal lines on our acceleration graphs. Now you're ready to complete additional practice work interpreting graphs of motion. Make sure you follow the Learning Target Requirement Sheet and complete the work as needed. Thanks!